This video is sponsored by Squarespace.
So I recently learned about this proof of the irrationality of E, and I thought I'd make a video about it. So this is due to J. Sondow, and you can find it on the archive. Here's the number. So this is maybe given as a geometric proof here, and it involves the geometry of the real line, in particular, something called the nested interval theorem. So it says that any intersection of nested closed intervals is non-empty. And here's maybe a way of stating that if you want to explicitly write down what those closed intervals are, making sure they're nested, of course. Okay, so keeping in mind that we want to use this nested interval theorem, at least in the background, well, we need to construct some nested intervals. So how might we do this? Well, also keeping in mind that we want to show that E is irrational, perhaps E should be inside of all of these nested intervals. So what's maybe the simplest closed interval that E is a member of? Well, I think it would probably be the closed interval that starts at 2 and ends at 3. And that's because it's well known that E is between 2 and 3. So that's exactly how we'll define I sub 1. And now we've got to figure out some sort of recursive method for defining the rest of the intervals. And maybe here's how to do it in a two-step process. So let's divide I sub n minus 1 into n equal subintervals. So that's the first step of this two-step process. And then how do we define I sub n? Well, this is how we'll do it. We'll set I sub n equal to the second of these subintervals, where when I say these subintervals, I mean, well, the ones that we defined right above. Okay, so let's make a little picture of what's going on, as well as a calculation as to some of these subintervals. So let's get a picture of I sub 1 on the board. In other words, the interval from 2 to 3. Then let's also write it down here. So we've got, like I said, I sub 1 is equal to the interval from 2 to 3. And then since we construct I sub 2 by splitting this into 2 equal subintervals and taking the second, we probably want to get a denominator of 2 in here. So let's notice that this is the interval 4 halves up to 6 halves, kind of clearly, which we can pull apart into 2 equal subintervals easily now. So this is 4 over 2 to 5 over 2, union 5 over 2 up to 6 over 2. And since we want the second by our rule, this guy right here will be I sub 2. Okay, so now let's get on that on the board. So we'll go right in the middle, which is maybe like, that's close enough. And we'll note that this is the point 5 halves. And then we'll make a little shading here in orange to correspond to that thing that I had right there. So there's our I sub 2. And now let's maybe bring this I sub 2 down, which we have, like I said, was 5 halves to 6 halves. And now we want to pull this apart into 3 equal subintervals. But that means we probably want to get a 3 in the denominator as well. So we can do that by writing this as 15 over 6 up to 18 over 6. Again, just by multiplying the denominator as well as the numerator by 3. But now we can pull this apart into 3 equal subintervals. We have 15 over 6 up to 16 over 6, union. So the next one will be 16 over 6 up to 17 over 6. And then finally, pretty clearly, 17 over 6 up to 18 over 6. Okay, so that's good. We've pulled that apart into 3 equal subintervals. And since our rule says we take the second one and define it as the next interval, that'll be I sub 3, that 16 over 6 to 17 over 6. Now let's do that over here. So we'll split this into 3 pieces. We won't be super careful about it, but we'll be kind of a little precise. So there's 3 semi-equal pieces. We'll note that this is 16 over 6 and this is 17 over 6. And we'll shade in the middle corresponding to the green color that we're using down here. So there it is. There's our I sub 3. Now let's bring that down. So we've got I sub 3, is equal to 16 over 6 and then 17 over 6. Now we want to split that into 4 equal subintervals. So that'll be 64 over 24. I guess I should say we want to introduce a denominator of 4 now, so we'll multiply by 4 over 4. And then the next one is 65 over 24. Union, then we'll have 65 over 24 to 66 over 24. And then next we'll have 66 over 24 to 67 over 24. And then finally rounding that out will be 67 over 24 to 68 over 24. And that's the complete dissection of I3 into 4 equal pieces. Okay, so let's see. The second one will be this one right here, given, we want to take the second one. That's kind of our rule. So we've got I sub 4 as that. Now let's go up here. So splitting this into 4 equal pieces, this will be our I sub 4. So I won't bring the endpoints up, but that's what it is. And then you keep going and going and going and going and going. So let's look at these intervals that we have on the board. Let's maybe bring this I sub 4 down first. So that's 65 over 24 up to 66 over 24. Let's put a box around these. And what we'd like is to get some sort of closed form for these intervals, and we'll prove the closed form. Okay, so looking at this, well, what do we have? Notice here we've got a denominator of 1, which is like 1 factorial. Here we have a denominator of 2, which is 2 factorial, denominator of 3, which is 3 factorial, denominator of 4, which is 4 factorial. Then we just have to figure out the numerators. And if you squint at it for a little bit and maybe play with some numbers, keeping in mind the famous series definition of E, what you'll see is that I sub n should probably take the form of S sub n and then S sub n plus 1 over n factorial. And this is, of course, where S sub n is equal to the sum as m goes from 0 to n of 1 over m factorial. So it's like the nth partial sum of the series that creates E. Okay, so now let's maybe prove this on the next board.
Before we continue, I'd like to thank today's sponsor, Squarespace. Squarespace is a service that takes the hassle out of creating a website. You don't have to be a programmer or a graphic designer to have a professional-looking website. Because of their support, I can dedicate all my spare time to doing the things I love. With Squarespace, you too can focus on what's important to you and leave the technical stuff to them. With the new Fluid engine, you have complete control over the structure of your website. The simple drag and drop action will help you get your site online quickly, and access to analytics will help you tailor your content to your audience. I use Squarespace for my website, and I find it easy to use with plenty of integrations. They even have a plugin for LaTeX that allows me to write equations very easily. Whether you need a place to sell your merch or show your art, Squarespace has the tools you need to keep your website modern and easy to use. So what are you waiting for? Give Squarespace a try by going to squarespace.com/michaelpenn to save 10% off your first purchase of a website or a domain using code michaelpenn. Thanks once again to Squarespace for sponsoring today's video that we are now returning to.
Okay, so we kind of guessed the form of the nth subinterval in the last board, and now we'd like to prove that by induction. Notice we don't really need a base case, and that's because we checked that for a couple of the smallest cases already to get an idea of what's going on. Now let's suppose for some k bigger than or equal to 1, we know that I sub k has the right form. In other words, it has left-hand endpoint sk and right-hand endpoint sk plus k factorial. That's the so-called induction hypothesis. Now let's dissect I sub k into k plus 1 subintervals. And that's just based off the rule that we use to create I k plus 1. So notice that'll start at sk, and then the next one will be sk plus 1 over k plus 1 factorial. And I guess I should say that's because this interval, I sub k, has length 1 over k factorial. So if we're going to split that into k plus 1 subintervals, then we're going to get one of length 1 over k plus 1 factorial. At least the subintervals will be that. Okay, so that's our first. And then the second will be sk plus 1 over k plus 1 factorial. That's the left-hand endpoint. and then sk plus, well, it's really 2 over k plus 1 factorial, but I'm going to write this as 1 over k plus 1 factorial plus another 1 over k plus 1 factorial, and then union dot dot dot. We don't really need the rest of them because the second subinterval will be the one that we need. So now let's maybe take this subinterval and view it two ways. So by our defining procedure, we know that this is equal to I sub k plus 1. But then also, by the rule that defines the s sub n's, it's pretty clear that s sub k plus 1 over k plus 1 factorial is simply sk plus 1. But then we see that this is sk plus 1 plus the next thing. So sk plus 1 plus 1 over k plus 1 factorial. Oh, so following this little like triangular equality, we have exactly what we need to finish this proof by induction. So the next step is to finally get E into the mix. We'll show that E is in fact in every one of these. So showing that E is in the intersection as n goes from 1 to infinity of I sub n will really be equivalent to showing the following inequality. So this is if and only if, you know, for all natural numbers n, we know s sub n is really less than or equal to E, but we'll prove a strict inequality. So less than E, which in turn is less than s sub n plus 1 over n factorial. Okay, so that's our equivalent statement, which we'll prove. Okay, so let's maybe get to that. So let's take s sub n and write it via its definition. So this is the sum as m goes from 0 up to n of 1 over m factorial. But that's going to be strictly less than what we have if we just extend this to an infinite sum. I think that's pretty clear because, well, this is a sum of all positive terms. So the sum as m goes from 0 to infinity of 1 over m factorial. Oh, but that's equal to the number e. Kind of famously, that's the series definition of e. But now let's write e like this again, but let's split it into pieces. So let's split this into the sum as m goes from 0 to n of 1 over m factorial plus the sum as m goes from n plus 1 up to infinity of 1 over m factorial. That's just splitting this sum into two pieces. Okay, but let's notice that this is simply equal to s sub n, that's the first one, and then plus the sum as m goes from n plus 1 to infinity of 1 over m factorial. I just copied that one over. Now we'd like to start manipulating that second thing right there. So let's bring it down. We have this is equal to s sub n plus the sum as m starts at n plus 1 and goes to infinity. And let's notice that n plus 1 factorial is a factor of everything down there, given that that starts at m equals n plus 1. So that means we can factor that out. So we have 1 over n plus 1 factorial as a factor, and then left over will be the product starting at n plus 2 and ending at m. And now I think it's kind of important to notice how many terms we have here. And by a simple counting argument, there are m minus n minus 1 total terms. Now we're going to start inequality arguments. So this is strictly less than Sn plus 1 over n plus 1 factorial times the sum as m goes from, let's see, n plus 1 up to infinity of 1 over n plus 1 raised to the m minus n minus 1. Let's maybe talk our way through that. Well, I replaced every one of these terms with something larger. N plus 1 is larger, but that makes the whole thing smaller. Okay, good. But next up, we can maybe do a change of index here. I don't think we really need to do a change of index, but we can replace all of the m's here with m plus n plus 1 and make that look a little bit nicer. So let's see. Now we'll just bring some stuff down. We have Sn plus 1 over n plus 1 factorial. And now that'll be the sum as m goes from 0 up to infinity of 1 over n plus 1 raised to the mth power. But that's a geometric series, and we know the sum rule for a geometric series. So using that, we have Sn plus another 1 over n plus 1 factorial, and then 1 over 1 minus 1 over n plus 1. But now a pretty simple simplification will allow us to write this thing in the green box as n plus 1 over n. So in the end, we have this is equal to Sn plus 1 over n times 1 over n factorial. Just after a little bit of simplification, but that's pretty clearly less than Sn plus 1 over n factorial. And now let's underline everything we needed here to, finish this argument which is happening in the yellow box. So we've got Sn right here. We've got a strict inequality right here, the number e right here. Let's see, another strict inequality right here, and then Sn plus 1 over n factorial there. So that's exactly the inequality from the yellow box, which, like we said before, is equivalent to e being inside of all of those. Okay, let's keep going. So our next claim will essentially finish our argument. And that is that the set of all rational numbers intersected with the intersection of all of our intervals is empty. Okay, so let's maybe see how this may go. So let's first note that if we have r over s, which is a rational number, we can write r over s as a rational number where the denominator is a factorial. So that would be r times s minus 1 factorial over s factorial. And I guess maybe we should say that that's equal to r over s. Okay, so maybe what's really the takeaway from this? The takeaway here is every rational number can be written with a factorial denominator. Great. And we're going to use that, little fact about rational numbers to show that this intersection is in fact empty. And we're going to do that by way of contradiction. So by way of contradiction, let's suppose that a over m factorial is inside of this intersection. So we've got the intersection from 1 up to infinity of I sub n. Again, this may not start seeming super general, but by this little orange box over here, we know that this could be a representation of any rational number. Okay, but what does it mean to be in an intersection? It means that you're in all of the components. So that means that a over m factorial is in fact inside of im plus 1. But then what was im plus 1? That was equal to the closed interval starting at sm plus 1 and ending at sm plus 1 plus 1 over m plus 1 factorial. But then let's notice that that's completely contained within I sub m, and we can even throw away the endpoints. So in other words, we've got this containment which shows us that this closed interval is inside of the open interval Sm to Sm plus 1 over m factorial. Great. So pushing that into an inequality, we see that Sm is strictly less than a over m factorial, which in turn is strictly less than Sm plus 1 over m factorial. And then multiplying through, okay, so clearing the denominators, we see that m factorial times s sub m is strictly less than a, which in turn is strictly less than m factorial times s sub m plus 1. Okay, but putting that back into terms of an interval, we know a is on the following open interval. So it starts at m factorial s sub m, and it ends at m factorial s sub m plus 1. But then also, by our kind of construction of rational number up here, we know that a is taken to be a natural number. So that means that this is also intersected with the set of natural numbers. But that's a problem, because these are consecutive natural numbers. And since we have an open interval, well, there are no natural numbers between those two consecutive natural numbers. So that means this is in fact the empty set. So we've got an element of the empty set, which is a contradiction. What does it contradict? Well, it contradicts this assumption right here that we were able to find a number of the form a over m factorial within that intersection, which means that's in fact impossible. So pushing that all the way to the top, that means the intersection of the rationals with our intersected intervals is in fact empty. Oh, but E is within this intersection. But the intersection does not intersect the rationals. That means that E must be outside of the rationals. So these two things together tells us that in fact E, it cannot be a rational number. So what did everyone think about this proof? I think it's really nice. And if you're still around and you haven't subscribed, maybe consider subscribing. It would really help us out. And that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.